So I'll speak about AI machine learning just as Misha did. Of course, AI is a big revolution in computer science and in most of the other sciences. To make the point, I was in Stockholm at the ceremony of the Nobel Prize because an ex-postdoc of mine, Demis Hassabis, got the Nobel Prize for AlphaFold, which solved this decades-long problem in biology, the one of predicting the 3D structures of proteins from the sequence of amino acids. And so it's invading all sciences, and of course AI is really machine learning. And it was, I think, pretty clear to a number of us, including Steve, at least a couple of decades ago or earlier, that the problem of learning is the gateway to the problem of intelligence. And personally, I think that the problem of intelligence is not only one of the great problems in science, like the origin of life or the origin of the universe, but it's the greatest of all, because if we can make progress in it, then we can more easily solve all other great problems. So anyway, back in the 2000, this was by Felipe and Steve, was I think the first paper to introduce learning into serious mathematics. So this was turning point. And but at the time, and I go to, before that, I will give you something that you all know, but just as a refresher, what are deep neural networks today are several layers. For instance, for classifying an image, the input is an image, and then you have several layers of neurons, so-called, which are simply units that take the weighted sum of their inputs, which come from if this is the first layer, come from in this case, the image, if not, from the output of the previous layer. And so take the sum, and it's a weighted sum. There are weights on each of this line, pass it through a simple nonlinearity, which may be of this kind, like the RLU, but it's not critical. And the problem here is how to set the weights. And so the way it is done is by having a training set of inputs and output, xi, yi, and computing a loss function. So the discrepancy between the prediction of the network for the same input with respect to what is true in the training set. And so you have a loss function, and you are trying to find the weights that minimize this loss function you could do it randomly, but trying random numbers, but of course this would be very inefficient. Though it's done usually using a variation of gradient descent, which is stochastic gradient descent, in which you don't use the old training set, but just a random subset of it. And in the meantime, this multi-layer perceptron optimized by gradient descent is also the key part of other architecture. One is the transformer, in which, in addition to this multi-layer perceptron, there is an initial layer that is doing a kind of self-attention, choosing which words are important for predicting the next word. And I will argue later that the key magic of a transformer is this autoregressive framework in which the system tries to predict the next word, but not that word at the end. This would be much more difficult. It's doing this in an autoregressive way. And there are other architectures like diffusion models that, for instance, in this case, take a single picture of me and then under an appropriate prompt generate the rest of the sequence. This is all virtual. Okay. Now, I want to go through a few steps. Essentially, it's a complementary view to what Misha said about curse over dimensionality and how this tells us something about current techniques like transformers and so on. So, and the question that I think we can answer in theory is, why do kernel machines suffer from the curse of dimensionality? Why deep nets can represent very high dimensional functions? Why is depth, multiple layers is important? Why convolutional networks are so much better than dense network in many applications? What controls generalization? Generalization is just not fitting the training set, but being able to predict new data. And there are more philosophical questions, like whether real numbers really exist, or whether, and things like that. So, not sure the time will be enough, but first of all, this is the kind of very short conceptual framework, or the standard approach in machine learning. Is not the only one possible, but it goes like this. You have an unknown function that maps inputs into outputs. This is supervised learning, which is basically the core of everything. So you don't know the function, but you have input-output data. Ideally, you'd like to have a parametric family of functions that can approximate this unknown function, so that then you can fit the parameters from the training data. And the requirements on this family is that they should have the power of approximating a very large family of functions, and they should do that using a number of parameters that is not exponential in the dimensionality. Okay? All right, that's basically, and then if you want, you can study generalization properties and on what they depend. Okay, so curse over dimensionality, Misha already mentioned this, and here is an even stronger examples. You know, take CFAR images. CFAR images are actually pretty small. They're 30 by 30, so 1,000 pixels. Okay, now, curse over dimensionality type bounds are worst case, but they tell you that the number of parameters you may need to approximate a function, say a function in a Sobolev space, with an error epsilon, suppose epsilon is 10%, depends exponentially on dimensionality divided by smoothness, the highest degree of bounded derivatives. And let's take m equal to 1 just for simplicity. In the case of CFAR, you have 1,000-dimensional function that you're looking for. So you get a number like this. And just to remind you, the number of protons in the universe is 10 to the 80. So that's a big number. Okay, so the solution to this is actually compositionality. And compositionality is this, in mathematics, it's just you compose functions. It is also very important in natural language and so on. Is the idea of combining, simple things to have something more complicated. For instance, von Humboldt used this to describe language as the infinite use of finite means. You have a finite alphabet, a finite number of words, but you can compose essentially an infinite number of sentences. So I use the term sparse compositionality. I really mean compositionality, but it's important to you make a point clear that you are composing simple function. sparse function. So in particular, sparse function will be function with a small number of that depend on a small number of variables. And each one does not have the curse of dimensionality because the number of variables is small enough. And this is because every function is trivially compositional. You can compose with the identity. You can always, if you have a decomposition this is composition of function, you can always represent it as the composition of this function with other ones. So, all right. So now, we had an old theorem several years ago with Hrusikesh Maskar, an expert in approximation theory, saying that if you have a function that is compositional, in the sense I said, then using a deep network, you can avoid the curse of dimensionality. Essentially, think about a function like this. This is a binary tree. Let me see. I don't have a figure, okay, but I have a binary tree in which each node of the tree is a function of two variables. And we can prove that for a function of this type, the D that goes into the curse of dimensionality is not the dimensionality of the input to the tree, which can be as large as you want, but is 2. The dimensionality of the constituent function, which is the worst one. In this case, they are all two-dimensional. So in this case, using deep networks, you can escape the curse of dimensionality for compositionally sparse function. Okay, now, let me give you what was not clear at the time is whether this assumption of having compositionally sparse was very special, dependent on properties of physics or something, or not, and looked pretty special, but pretty strong. But the answer is actually not. It's pretty generic property, and in order to do this, let's have a couple of definitions. First, just defining compositional sparse function. This is repeating more formally what I said. That is, it's a function where the constituent functions are, each one does not have the curse of dimensionality. And I can always represent a compositionally sparse function as a directed acyclic graph, where each dot here is a function, in this case of 3 variables, 2 variables, and so on. And the important, another definition is that standard definition is that I define a function to be efficiently Turing computable if it's computable by a Turing machine in polynomial time, no worse than polynomial time. Okay, so essentially a function that is efficiently Turing computable can be approximated by a Boolean function in P. P is Boolean function that are efficiently computable in polynomial time. Okay, so there is this theorem that tells us that if a function is efficiently Turing computable, then it's compositionally sparse. And one simple way to think about it is that I can always translate a Turing machine, a program, into a sequence of linear threshold functions. And And each one of them is sparse. So that's the first part. And the second one is that for each sparse compositionally function, there exists a deep network that approximates it arbitrarily well, without curse of dimensionality. So, these are examples of compositional function. This is the one that I was mentioning before of a binary tree, where you can have as many inputs as you want, so the dimensionality is as high as you want, if you make it deep. But each of the constituent function has dimension 2, and for this, the curse of dimensionality is 2. So depth is a key to avoid the curse of dimensionality. Kernel machine cannot avoid it in general because they're single layer, essentially. And this is, it also implies something else. So far I told you essentially existence results. And in a bit I'll tell you whether you can find this decomposition that is sparse. So optimization. But before going into that, I want to mention that if you have a network, a deep network, that approximates layer by layer a sparse decomposition of your function, which it does when you reach zero empirical error, which often happen, then this implies that you should have sparsity in the weight matrices. In other words, that each neuron will be connected as inputs to a small number of neurons, no dense connection. And in fact, we found that if you take sparsity of these weight matrices into account, then you can get standard Rademacher bounds, complexity bounds on the networks that are, 1,000 times better than the standard bounds with VC dimension or standard bounds with Rademacher complexity that did not take into account sparsity. And so we get now bounds that instead of being essentially loose, are actually still loose but not vacuous by 1,000. They're close to 1 as opposed to be 1 million or 10,000. Anyway, I don't want to waste time here. But I want to say that sparsity is really a key for approximation and for generalization. The question really is optimization. How can you find the correct decomposition of an unknown function? Okay, of course, you can try, but so far, I think we basically answer a lot of this question. Maybe not the last one, but and now about optimization. One interesting point is that a compositionally sparse function, say a Boolean function, may be difficult to learn in general because we know that we cannot learn every function in P. So P are essentially efficiently computable functions, but they're not in general learnable because otherwise this means that you could break encryption. And then as a consequence, P would be equal NP, that very few people believe to be true. So not all functions in P are learnable, but you can think of P as the set of sparse Boolean functions, depends on a small number of variables, and compositionally sparse, which are the composition of sparse functions. So this compositionally sparse function, in general, you cannot learn it if you have only input-output data. But if you have input-output data for each of the constituent functions, then you can learn them because they are sparse. And normally, sparse Boolean function can be learned most of the time. So the fact is that it's difficult to learn the whole function f if you have input and output of f, but it's usually easy to learn each of the G1 and G2 and so on if you have their input-output. And of course, in fact, from the theorem I showed, you can prove this theorem that was independently proven a couple of years ago by Aaron Malak, that every function that can be efficiently computed by a Turing machine, there exists a data set such that training an autoregressive next token predictor result in a predictor that approximates f. So you're basically learning the constituent function one by one, right? It's like if each word were a token in this theorem, then you'd have the training set to learn it. And that a token is, a word is more than, a step in a Turing machine. But, so you cannot do that exactly for words. But training on predicting the next word is what makes the problem much more easy to solve. Okay, now, I think, there is more to be done, of course, but this one of compositional sparsity and autoregressive could be some of the principles important for learning. And I think we are at a time in which we have for the first time, we have different minds, not only ours, but the various LLMs that we can study. And so I think there is an urgent need. I'm echoing what Misha said, to understand why they work as well as they do. Understand at least some of the principles. Because, soon it may be too late. So that's the main motivation. So that's, I think Volta invented basically electricity in 1800. Until then, there were sparks. Until then, information was traveling at the speed of a horse. This was 1800. It was made count by Napoleon. He published this discovery of the pila, the battery, in the Proceedings of the Royal Society. After him, there were very soon a lot of applications. The telegraph, electric motors, electric generators, electrochemistry. But until the 60s, 1860, nobody really understood what electricity was. There was no theory. A lot of application, no theory. It was Maxwell in 1864 that finally gave a theory of electromagnetism. And then, of course, more applications. And I think we are between Volta and Maxwell for machine learning. I hope we will have enough time.
Any questions?
So you need, to get an efficient learning system, then you need a combination of sparsity and depth. Is that correct? So the way you construct the network has to be sparse in some sense, composition. Is that the message?
So right now, the big problem is the optimization part, right? You can choose, we know which kind of parametric functions. They are basically deep networks with multiple layers, but it's unclear how to learn effectively the weights and which one should be 0 or not. For instance, in a convolutional network means that each unit is looking only at a small number of units in the layer below. All the other ones are 0. And this one, it's very difficult to learn if you start from a dense network. So typically they've been done by prior information that people thought this was a good architecture and they work well. It'd be nice to have a general algorithm approach to so powerful that can set the architecture to be a correct one, can learn the architecture. But a transformer may be doing something of that, and partly because they have a lot of training examples. But this one of optimization is the part which is quite mostly still open.
So I have my question is like what kind of uniqueness results do you have about
Which kind of?
What about uniqueness results that you have about this compositional representation? Because I imagine that a single function can have many different representations, right?
Right.
And like, is there some property that the network like?
So that's essentially the big question, right? It's the composition are very non-unique. And we know that, for instance, the most sparse one in terms of inputs is essentially a representation in which you have only units with 1 or 2 inputs, basically doing AND or NOT. And you can make a Turing machine out of it. So this is the kind of the representation in which you have maximum depth, but very low sparsity. And then there is everything in between. And so I think in a transformer, probably the ideal situation would be the one in which you have learned in pre-training simple but not too simple functions that then you can compose to have more complex functions when it's needed or at post-training. But how to do that in a rigorous way, it's totally unclear. People are basically trying to do this using different techniques like reinforcement learning and various other ones. It's a little bit like when children go to school. You start having a curriculum of learning. You start learning some of the basic things, basic skills, and then you're going to build on them for having more powerful skills.
Thank you, Professor Poggio. And I wish we had more time for you.